Hello and welcome to this film, which is all about Gibbs free energy and equilibrium. And in this film we're going to try and link two topics, the equilibrium topic, which you might be studying at the moment, and the energetics topic, which you may have studied in the past. Okay, and hopefully we're going to see in this film that there's a relationship between the equilibrium constant for a reversible system and the Gibbs free energy change for the reaction. And what we'll also hopefully be able to see is how we can connect the Gibbs free energy change with the yield and the entropy in a reversible system. Okay, so to begin with, we'll have a quick reminder of something that you might have studied in the energetics topic, and that is this equation that links the Gibbs free energy change for a reaction with the enthalpy change for a reaction and the entropy change for a reaction. And you might also remember that if a reaction is going to happen spontaneously, then the Gibbs free energy change must take a negative value. Now, how does that connect with what we've been learning about in equilibrium? Well, we know that if you take a reversible reaction system, like this one here, where nitrogen and hydrogen are reacting to produce ammonia, or alternatively ammonia is reacting to produce these things, then we will reach a position of equilibrium whether we start with pure reactants, so just nitrogen and hydrogen, or if we start with pure ammonia. Now we know that this position of equilibrium depends to some extent on the conditions that we use, but if we can get there spontaneously, either from the reactant side or from the product side, then that must mean that when we get to equilibrium, the free energy is at a minimum. Okay, because the free energy must be falling if a change is going to be spontaneous. And if the free energy is at a minimum, well then the entropy at this point must be at a maximum. Because if delta G is going to have its smallest value, then we want the entropy change to have its biggest value. Okay, because we're always subtracting this product of temperature and the entropy change from the enthalpy change. So if we want this to be as small as possible, the entropy change must be as big as possible, and so the entropy must be at a maximum at this point. Now we don't really have to do a lot with the maths in this particular context. It's just good to have an idea that when we are at equilibrium, the free energy is at a minimum and the entropy is at a maximum. And where we do have to start doing some maths is when we start connecting the free energy change for a reaction with the equilibrium constant. Okay, so here is an equation which is very important and allows us to make that connection. Okay, it says that the free energy change is equal to minus the gas constant, 8.31, multiplied by the temperature in Kelvin, multiplied by the natural logarithm, that's what ln is, of K. Okay, now you don't really need to worry too much about what the natural logarithm is or means, because there's a button for it on your calculator. But what we do have to do is watch out for units here, because delta G will normally involve the units kilojoules, whereas R involves joules. Okay, it's 8.31 joules per Kelvin. Okay, so now here temperature also is important to remember that has to be in Kelvin, but we should be pretty used to that by now. Okay, so watching out for those units, let's see if we can calculate the value of delta G at 20 degrees Celsius, given that the equilibrium constant for a reaction is 5.06 times 10 to the minus 15. Okay, so how are we going to do that? Well, we're going to say that delta G equals minus 8.31, because that's the gas constant, multiplied by the temperature in Kelvin, so 293 Kelvin, multiplied by the natural logarithm of this number, 5.06 times 10 to the minus 15. Now, in case you can't do that in your head, we can use our calculator, and we'll find that the answer to that is 80,148. Okay, so three significant figures, 80,100, or in other words, 80 kilojoules per mole. Okay, so the free energy change for that reaction is 80 kilojoules per mole, and that's positive. And does that make sense based on what the information in the question tells us? Well, if we've got a positive free energy change, then this means that the reaction isn't very likely to happen. Does the equilibrium constant tell us the same thing? Well, we've got a very, very small value for the equilibrium constant here, which means that hardly any of the reactants have turned into products. So yes, our answer does make sense. And to give you just a rough idea, if you get a value that is either plus or minus 20 kilojoules or more for the free energy change in an equilibrium system, that means we lie almost completely over to the reactant or the product side, depending on whether this is positive or negative. Now, doing the same kind of problem but in reverse, so now we're going to calculate the value of K given information about delta G. We need to know something about log rules here. I'm not going to go into this in a great deal of detail, but if natural logarithm of x equals y, then e to the power y equals x. And that allows me to rearrange this formula to say that ln k, well, first, this rule doesn't allow me to do this, but first of all, we can see that ln k is going to equal delta g over minus rt, or minus delta g over rt, it's the same thing. And if that's true, then k, now using this log rule here, k equals e to the power minus delta g on rt. Okay, so now we can plug, again, numbers into our calculator, and we can say that this is going to equal 60,000, because we've taken the negative of negative 60,000, remembering we're in kilojoules here, we're doing everything in joules because R is in joules, over 8.31 times 298, and once we've found this number, we're going to raise e to the power of that whole thing. Okay, and we can do that on our calculator. We just say e to the power of that, and that equals 3.33 times 10 to the 10. Okay, which is a very large number. And if k is very large, that means all our reactants have turned into products pretty much. And that's what's indicated by the sign of this delta G. It's negative, and it's quite a large number. It's 60 kilojoules per mole. Okay, so having done a couple of calculations, let's just see if we can get an idea about what G tells us about K just at a glance. Okay, so if delta G is positive, right, a reaction isn't likely to happen spontaneously, which means not many of our reactants are going to turn into products, and K will be small. Okay. On the other hand, if delta G is negative, then a reaction is likely to happen spontaneously, and in other words, our reactants are likely to turn into products, and K will be large. Okay, so our equilibrium constant will be large. Right. Anyway, hopefully that all makes sense, and hopefully you can see how the equilibrium constant is connected to the Gibbs free energy change, and you can see the relationship between delta G and yield. Didn't really talk about yield much there, but remember, if you've got a high yield, that means you've got a big equilibrium constant, and the entropy in a reversible system. If you've got any questions or comments, then please feel free to come and see me or to post a comment on YouTube.